Our start presentation. Hello, everyone. I'm Hyunsik Yoon from Seoul University of Science and Technology. I would like to thank to Sergey for inviting me to the conference. Today, I'd like to talk about fabrication method of the liquid repellent structures by capillary wrapping on the microscale arrays.
Henry, sorry to interrupt you. Am I allowed to record your presentation or not? Because I'm
sure, you can.
Okay, thank you. Sorry.
As you may know, there are many studies on liquid repellency structures. The most famous one could be the lotus leaves. The liquid repellency is very important for the lotus leaves because they can remove the dust. The dust can prevent the photosynthesis of the plant. So we call it the self-cleaning effect. When we examine the structures, the surface of the lotus leaves, we can find the micro and nanoscale structures like this. Another example could be the insects. We can see the insect, the structures, we can see those kinds of the micro and nanostructures. And the insect can want to prevent want to repel the liquid because those kinds of moisture or water can prevent the movement of the insect. And when we see the structures, we can see there are some special structures. We call it the re-entrant structures. The top surface is wider and the bottom it is narrowed. When we study the liquid wetting, many researchers are using the static model of Young's equation like this. As you can see, we place a liquid drumlet on a surface and measure the contact angle. And when the contact angle of the liquid is lower than 90 degrees, we can think that the solid surface are like the liquid. For example, when the contact angle is higher than 90 degrees, we can think that the solid dislike the liquid. Therefore, for the application or for the super oleophobicity or super hydrophobicity, we use the textured surface. In the case of the textured surface, there are two different models, like the Wenzel state and Cassie-Baxter state. In the case of Wenzel state, the interfacial area between the solid and liquid are very large, increased, and there is the effect of the amplification of wetting properties. However, because of the large surface area, interfacial area between the solid and the liquid, it is not good for the liquid repellency from the solid. So in case of the Cassie-Baxter state, there are the liquid can float on the air, and the air can be trapped on the structures. So it is easier to repel the liquid in the Cassie state. So we need to make the structure for the Cassie-Baxter state. In the case of the superhydrophobicity, it is a little bit simple. As you can see, the inherent contact angle of the liquid like water on a surface could be higher than 90 degrees in case of water because the water have the high surface tension. So as you can see, when we use the straight line like this, it is enough to trap the air between the solid and the liquid. On the other hand, when the aspect ratio defined as H over W is lower, the the liquid can contact on the ground of the structures, and then the liquid can wet the whole surface. So that's why for the superhydrophobicity, dense or taller structures is necessary, and they can show the superhydrophobicity. However, you can guess the taller or high aspect ratio structures is very weak in shear stress. For example, we can use the liquid repellent structures in the daily life applications such as protection films or car windshield or solar cells. In case of protection film, we have to rub with our fingers, and if there are some high aspect ratio structures on the surface, it can be broken easily. In the case of car windshield, as you know, there are some shear stress to remove the rain. So that's why the robustness is very important for the liquid repellency structures. So that's why many researchers have moved the research focus of the hydrophobicity from the fabrication of the artificial structures to the robustness of the structures. For example, very recently, a paper was published in Nature. They used armored strategy like microstructures, embedding nanostructures. They can be used for the daily life because they can be very stable during the aberration test. Unfortunately, in case of the oil repellency, it is a little bit different. In case of the oil, the inherent contact angle, like this, the contact angle is always lower than 90 degrees in any solid surface. So that's why when we use the straight line, the surface can be wet by the liquid. So that's why there are some methods to make those kinds of inverse tapered structures. For example, if the contact angle is higher than the taper angle defined like this, we can trap air between the solid and the liquid. It is very important to the liquid repellency from the solid. So we have to reduce the alpha, the taper angle, to be smaller than the flat, the contact angle on a flat surface. So that's why many research groups try to make the many structures like the tapered structures or reentrant structures or hood structures or doubly reentrant structures designed by the UCLA group. Those kinds of reentrant structures can be used for omniphobic surfaces without coating or for any liquid. For the fabricating, for making the microscale structures, many research groups use the photorisography. Photorisography used the mask and UV light, and when with the UV light transmitted through the transparent region of the mask, the polymer material, the chemistry of the polymer material can be transformed, and the transformed polymer can be removed by a solvent because of the difference of the solubility. So after that, we can get is the two-dimensional structures. However, to make those kinds of the hood structures or sheriff T structures or very special structures to trap air and to prevent the the wetting of liquid, it is not enough in the case of the photoresorography. So in the review paper, okay.
Yes, yes.
In the review paper about the oleophobic surfaces, the author claimed that the fabrication should be as simple as possible and easily to be repeatable, and the durability or the mechanical strength of the surface is very important. Okay, so that's why I use the soft resorography and replica molding method for the easy fabrication in a chip method and for making the three-dimensional structures. I use the polyurethane acrylate polymer, which has double bond, and also I use the perfluoropolyester polymer. The commercial name is MD700, and we use the liquid pre-polymer mixed with the photo initiator, and we fill the liquid pre-polymer onto a master, and we expose the UV light. During the UV radiation, there is a free radical polymerization, and they can be solidified, and we can get the solid of the replica structures. And also, after the preparation of the master, we can get a replica mold, and as you can see, it is the inverse image. And then, if we can replicate again from the first replica, we can get the same shapes from the master original structures. For the replication of the three-dimensional structures, we use the PDMS, polydimethylsiloxane. Our group published it about 10 years ago about the replication of the three-dimensional structures with PDMS to make those kinds of the reversibly inversed structures. So after the preparation of the master with the whole array, we pour the liquid pre-polymer, and the liquid pre-polymer can be cross-linked by UV light, and then we detach the micropillar array from the master, and we can get the micropillar array. This one is the micropillar array, and it is the two-dimensional. For making the re-entrance structures, we use the capillary wrapping. For the capillary wrapping of the liquid pre-polymer on a micropillar array, we coated the liquid mixture, liquid mixture with isopropyl alcohol, and then we contact the micropillar array on a liquid. Then the liquid can be coated on the micropillar array, as you can see, and we can get the hyperbola pattern. The yellow area is the original micropillar array, and as you can see, the sidewall are coated or wrapped by the capillary burst with the liquid. So we can, to control the shape, we can use the different shape of the micropillars, or the shape means the space ratio, and we can control the thickness of the liquid polymer. And after contacting the micropillar array, we can get many these liquid prepolymer can wrap around the micropillar array. We can get a condition to make the hyperbola structure or mushroom structures from simple mass balance. And interestingly, we can get the result of two different systems. Like when the aspect ratio is high, it means the height is taller. And if there is a meniscus formed on a surface like this one is the liquid. And as you can see, we define the meniscus height Z like as shown in this figure, and the Z can be obtained from the contact angle and the distance between the pillar array. And if Z meniscus height is higher, the lower than the pillar height, we can guess the meniscus can be formed like this. And when we detach this structure from the silicon wafer, the substrate, we can get the connected structure. On the other hand, when the height is lower than the meniscus height, as you can see, the meniscus height is higher than the height. The liquid can wet on the roof of the surface. Then after the capillary capillary wetting, we can get these kinds of the hyperbola structures after detaching from the silicon wafer. And those shape can be controlled by the contact angle of the liquid on the surface, and as well as the thickness of the initial prepolymer, the thickness. This one is the experimental result. We vary the space ratio from 0.5 to 6, as you can see, and we control the thickness of liquid prepolymer from 0.6, 0.86 to 5.2 micrometer. As you can see, the top area are connected when the space ratio is small, and it means the height, the aspect ratio is higher than the meniscus height, and the parents are separated when the space ratio is the higher, and also the diameter of the separated hyperbola structures increased when we increase the thickness of the liquid polypolymer. From the mass balance, we can get those kinds of the graph, and the red area shows the connected area, and the green region we can obtain the mushroom structures like this, and also the blue area we can get the hyperbola structures like this. As you can see, the operation window or the condition for obtaining hyperbola structure is very wide. It means that we can obtain the hyperbola structures very easily. Also, by just using the simple mass balance, we can obtain the graph of the diameter and the thickness or the space ratio. So as you can see, the diameter can be the diameter are increased with increasing the initial thickness, and when the space ratio is higher, the diameter increased as well. So I explained the mushroom structure or hyperbola structures could be used for the oleophobic or oil-phobic surfaces. So that's why after the preparation of the hyperbola structures with different thickness of the liquid polymer and a different space ratio, as you can see, the contact angle with the hexadecane, as you can see, the contact angle is very, very high when we use the dense hyperbola structures. And also, as you can see, it is the transparent, and the hyperbola structures can show the liquid repellency with water and hexadecane and oil. So we can think that these structures can show the repellency of, with any liquid. So I explained before, as I explained before, the important thing in the oleophobicity, we need a simple fabrication method. So after the preparation of the hyperbola structures, we use the replication method with PDMS and propylpolyester, which has the low surface energy. So after the preparation of hyperbola structures by contacting micropillar array on a liquid, then we pour the PDMS polymer and then cured and detached from the hyperbola structures. And then we we call the replica mold. From the replica mold we can get the shape of hyperbola structures with different materials like the MD700. This one is the example. In case of at first we used the polyurethane acrylate, and then the first replicated the structure is this one, and we can get the doubly replicated structures with fluoropolymer. And when we control the condition such as the space ratio, we can get the mushroom structures like this. And as you can see, the mushroom structures can be replicated by the soft PDMS. And the soft PDMS we used, we lower the ratio of the cross-linking density for the softness, and then we can get the mushroom structures from the PDMS. For the, I'm sorry, I think it is the previous version of the presentation for the talk. Okay, anyway, and then we wrote with key wipes for the robustness, for see the robustness of the oleophobic surface. And in case of hyperbola structures, after rubbing, the oleophobicity can be remained. On the other hand, in case of mushroom structures, after rubbing with kiln wipes, they can it is damaged and they are broken from the surface. So that's why the oleophobicity was destroyed. So when we see the the breaking point with a high shear stress, we can see that in case of the hyperbola structures, the breaking point is the center region. On the other hand, in case of mushroom structures, the breaking point is the bottom region. So that's why it can be applied by the high torque. So for the quantitative analysis, we load the weight on the surface on the film with the hyperbola structures. Then we pull pull on a sandpaper for applying the shear stress. As you can see, when we roll the 50 gram of weight on the 1 square centimeter, it is stable. On the other hand, in the case of mushroom structures, it is broken and it is damaged. Okay, I would like to wrap up the presentation with this summary. I talked about the motivation of liquid repellent surfaces inspired by nature, and we have to design the geometry for the liquid repellency. And there are some issues, especially in the case of super oleophobicity or the oil repellent surfaces. It is very, very complicated and it is difficult to make, and the durability is very important. So that's why I propose the hyperbola structures by using the capillary wrapping of liquid. And I show the omniphobicity, and I show the robustness by using the ablation test. This picture was taken 2 years ago, and this picture is the last picture without wearing mask. I hope to see you in person.